Hello everyone. In this video, I'll be talking about the Carnot engine. First, we shall see what we mean by reversible and irreversible processes. Reversible and irreversible process. A thermodynamic process is reversible if the process can be turned back such that both the system and the surroundings return to their original states, with no other change anywhere else in the universe. In the case of a reversible process, it is possible to bring back the values of the state variables back to their original value, that is, when the process started. But a reversible process is an idealized notion. A process is reversible only if it is quasi-static. That is, system is in equilibrium with surroundings at every stage and there are no dissipative effects. There are many dissipative effects like energy loss due to friction, etc. Hence, a reversible process is not possible in the real world. But we consider a reversible process in theory because the second law of thermodynamics rules out the possibility of a perfect heat engine with 100% efficiency. It turns out that a heat engine based on the idealized reversible processes achieves the highest efficiency possible. So, for determining a design for a heat engine having the maximum efficiency possible, we have to consider a reversible process. Now, the spontaneous processes of nature are irreversible. Irreversibility is a rule rather than an exception in nature. Irreversibility arises mainly from two causes. One, many processes like the free expansion or an explosive chemical reaction take the system to non-equilibrium states. Two is that most processes involve friction, viscosity and other dissipative effects. Now we shall see Carnot engine. What is the highest efficiency possible for a heat engine working between two reservoirs at temperatures T1 and T2? Sadi Carnot, a French engineer, first considered this question in 1824. And he was able to come up with an ideal engine operating between two temperatures. For the efficiency to be 100%, the ideal engine has to have a reversible process. Now, a process is reversible if it is quasi-static and non-dissipative, as we have already seen earlier. So, a reversible heat engine has to absorb heat from the hot reservoir and release heat to the cold reservoir isothermally for the processes to be quasi-static. If there is a temperature difference between the system and surrounding, this process cannot be quasi-static, as the system and surrounding will not be in equilibrium. Now, to ensure that the processes which is used to complete the cycle by taking the temperature from T1 to T2 and vice versa is quasi-static, it is better to assume that the process is adiabatic, since it involves no heat flow. So, considering this process which takes the temperature from T1 to T2 as an adiabatic process is much simpler. Hence, in the Carnot cycle, it consists of two isothermal processes and two adiabatic processes. Now we shall see the Carnot cycle. For explaining the Carnot cycle, we can consider a ideal gas enclosed in a cylinder having a frictionless piston. Now the cylinder is kept in contact with a reservoir, hot reservoir of temperature T1. Now we shall see the first process, that is the first isothermal process, which is the isothermal expansion of the gas inside the cylinder. This pushes the piston upwards and the volume of the gas inside the cylinder increases. And the PV graph is as shown, where the pressure of the gas decreases from P1 to P2 and the volume increases from V1 to V2. And since this is a isothermal process, the temperature T1 remains the same. Gas is allowed to expand adiabatically and the hot reservoir is removed. This is the case of the adiabatic expansion. And in this case, the gas inside the cylinder releases temperature T2 to the cold reservoir. Since an adiabatic process involves a flow of heat, so the temperature falls from T1 to T2. The pressure falls from P2 to P3 and the volume of the gas increases from V2 to V3. Now the next step in the Carnot cycle is the isothermal compression. In this case, work is done on the gas and hence the pressure of the gas increases and the volume decreases. And since the process is isothermal, the temperature remains the same. Now the final adiabatic process is the adiabatic compression, which results in bringing the system to its initial state. That is adiabatic compression. In this, work is done on the system to raise the temperature back to T1 and the pressure is increased back to P1 and the volume of the gas returns back to the initial starting volume, which is V1. So this is the Carnot cycle, and based on this Carnot cycle, Sadi Carnot proposed a heat engine having 100% efficiency. Now we can see how to calculate the efficiency of a Carnot engine. Now the work done in the first isothermal expansion, that is 1 to 2, Q1 is given by mu R T1 log of V2 by V1. Now the work done in the case of the adiabatic expansion, that is from W2 to 3, is given by mu R by gamma minus 1 into T1 minus T2. Now the work done on the gas in the case of isothermal compression, Q2 is given by mu R T2 log of V3 by V4. And the work done in the final adiabatic compression is given by mu R by gamma minus 1 into T1 minus T2. So the total work done in the case of a Carnot engine, W is given by the sum of all this work done in the cycle. That is, W is equal to W of 1 to 2 plus W of 2 to 3 plus W of 3 to 4 plus W of 4 to 1. and which becomes W is equal to mu R T1 log of V2 by V1 minus mu R T2 log of V3 by V4. Now net efficiency of a Carnot engine is given by the ratio of the work done to the heat given by the hot reservoir, that is W by Q1, and W is the total work done and it is given by the difference of Q1 minus Q2, which is the heat given to the heat released, which is equal to 1 minus Q2 by Q1. That is equal to, we have already have the values of Q1 and Q2. If we substitute that, we get 1 minus T2 log V3 by V4 by T1 log V2 by V1. It can be proved that V3 by V4 is equal to V2 by V1. And hence the formula of net efficiency of a Carnot engine becomes 1 minus T2 by T1. So this is the end of this video. In this video, I have discussed the concept of Carnot engine. If you have got any doubt in any of the topics discussed in this video, please comment in the section below this video. Thank you.